We're going to talk about division exponent rules in this tutorial. So you can see the first four problems here we've asked to simplify each by expanding. So when we see m to the seventh, that means that we are multiplying 7m's together. And that's in the numerator. And then in the denominator, we have m cubed. So m times m times m. Well, one thing that we know is that if you have something over itself, this simplifies to 1. So for each of these pairs of m's, where one's in the numerator and one is in the denominator, m over m simplifies to 1. So we have 1 and 1 and 1. So you can envision that up top we have a 1 over 1. And then we're left with m times m times m times m, which is m to the fourth. And on the bottom, this is just a bunch of 1's multiplied together, so it's m to the fourth over 1. And we can just say that our final answer is m to the fourth. If we did that with number 2, we would have w times w times w times w times w over w. One pair of w's from the top and bottom simplifies to 1. So again, we would be left with w to the fourth power in the numerator over technically 1, which we don't have to write in the denominator. You're probably starting to recognize a rule here, that if we divide two powers with the same base, so they each have a base of m, we can actually subtract the exponents. 7 minus 3 equals 4. 5 minus, this has an exponent of 1, equals 4. So our exponent division rule is x to the a power divided by x to the b power. Since they're powers with the same base of x, my final answer would have the base of x, and the exponent would come from subtracting this exponent minus this exponent. If you tried to use that rule over here, m to the fourth divided by m to the sixth, if you do 4 minus 6, you'll notice you're going to get m to the negative second power. And that's really something that we're unfamiliar with. If I try to think about something to the negative second power, for instance, 5 to the negative second power, I don't really know what that means. So I'm going to come back to that here in a minute. But let's try to expand it to see what this actually does mean. So m to the fourth is m times m times m times m over m to the sixth. So we have 6 of them on the bottom. So m over m is 1. So each of these simplifies to 1, or 1 over 1. And we can see that we still have m times m in the denominator. In the numerator, we would technically have 1 times 1 times 1. We would have a 1. So what we're left with here when we expanded is 1 over m squared. This is equivalent to m to the negative second power, and this brings up our negative exponent rule. When we have something, a power with a negative exponent, and right now this is technically in the numerator, right? This is technically like it's over 1. If you want to rewrite this so it has a positive exponent, you need to move it from the numerator to the denominator. So this means that m to the negative second power is equal to 1 over m squared. In the same way that 5 to the negative second power, if we wanted to, we could rewrite it as 1 over and move 5 to the negative second power to the bottom to become 5 to the second power, which means this is just 1/25. So rewriting it so that it has a positive exponent gives us meaning that we're able to make sense of. So what this means is that if you have something, a power to a negative exponent, then you could rewrite it as, let me move that out of the way, 1 over x to that positive exponent. In the same way, if you started with 1 over x to the negative exponent, so the negative power is in the denominator, you can move it to the numerator to make it a positive exponent. So w cubed over w to the eighth is technically w to the 3 minus 8 is w to the negative fifth power, but we know from our negative exponent rule that this is 1 over w to the positive fifth power. I like to always ask myself, where do you start with the most of your variable? So if you start with 8 w's multiplied together in the denominator, that means in your answer, that's where your w's should be located, because you had more of them when you started to simplify. So let's try a couple of examples together. For x to the negative third power, you have to remember that the exponent touches the base. In this case, it's touching x, but it's not touching the 4. So 4 is the coefficient. It's not part of the base, which means the only issue here is that we have x to the negative third power, and we're not going to allow negative exponents in any of our final answers. So that means that if I'm going to write this as a fraction, This is technically over 1 as it is right now. It's in the numerator. So the 4 gets to stay put. It's only the x to the negative third power that needs to move to the denominator so that it becomes x to the third power. And there's nothing else that we could do there. Let's look at number 6. Again, I usually write my fraction bar, and I think to myself, well, 10 is the coefficient. It's not part of the base, so 10 is allowed to stay put. 20 is a coefficient. It's not part of the base, so it's allowed to stay put. But x to the negative fifth, we want to rewrite, so we're going to move that to the bottom to become x to the positive fifth. And y to the negative eighth is currently in the denominator. We want to rewrite that in the numerator to become y to the positive eighth. Now, these are powers with different bases, so I can't simplify y to the eighth over x to the fifth. However, I do notice that we have 10 over 20. That's a fraction that can be reduced to 1/2. So I'm going to rewrite this as 1y to the eighth, and you can write the 1 or not, you don't have to, over 2x to the fifth. Looking at number 7, again, I just try to move things that need to be moved first, but you can also use the rule. So I'm going to show you both ways in this instance. So one way is if I'm using the rule, I'm just going to jump to my coefficients and think 40 over 55, how does that simplify? Well, they're each divisible by 5. So 40 divided by 5 is 8, and 55 divided by 5 is 11. And then if I use my rule, x to the 7th divided by x to the negative 4th, I could do 7 minus negative 4 and get x to the 11th power. But a lot of times we don't feel as confident, honestly, with the rules, which I know sounds a little bit weird, but sometimes it might have been easier just to expand it. So let me show you how I would have done that. So I would have done 40 and 55. Those get to stay put. X to the 7th, there was nothing wrong with that. The only thing that would have had to move is x to the negative 4th, and moving it up to the up to the numerator to make it x to the positive 4th. And now you might be able to see why this is x to the 11th on the top, right? Because if you're multiplying powers with the same base, you add the exponents, and then 40 over 55 reduces to 8 over 11. So you can do it either way. You could expand it out. You could use the rule. It's up to you. So why don't you pause the video, maybe try a couple of these on your own, and I'm going to quickly go through the answers then. So in this case, x cubed over w, those are different powers, and neither of them needs to move, or different bases so that they can't actually simplify together. So the only thing that I can simplify is 9 over negative 27 to get 1 over negative 3. The negative could be on top or on bottom. Negative 2/16 reduces to negative 1 over 8. P cubed over p to the 7th. Now, if you use your rule, you would do 3 minus 7, and you would get p to the negative 4th. And this would technically be up here, p to the negative 4th. Well, we don't want to leave that in our numerator with a negative exponent, so we would have to move that to the denominator to become negative 1 over 8p to the 4th. Now, again, that was using the rule. It might be more helpful to instead think of it as negative p cubed. Whoops, and I'll actually write out p cubed as p times p over 16, and then p to the 7th, you could draw out 7 p's multiplied together there and do your canceling to end up getting the same thing. This last one looks a little bit more challenging, but you have to think about just what is the base of each power. So 3x to the negative third power, 3x is the base. This needs to move. So 3x to the third power in the denominator. Y to the 4th doesn't have to move. Negative x squared, or really this is read as the opposite of x squared. This is the same thing as saying negative 1x squared. There's nothing wrong with that. So we can multiply by negative 1x squared on the bottom. Y to the negative 6th needs to move up to become y to the positive 6th. Well, y to the 4th times y to the 6th is y to the 10th. And then in the bottom, it might be helpful to expand this. So 3x cubed is 3x times 3x times 3x times that negative 1, and times x squared is times another 2 x's. Excuse me. 3 times 3 times 3. So 3 times 3 is 9, times 3 is 27, times negative 1 is negative 27. X times x times x times x times x is x to the 5th. Y to the 10th over x to the 5th cannot be simplified because those are powers with different bases. The last rule I want to talk about is if you have something like this, y cubed over y cubed. Well, there's two different things that I know. I know that if I use the rule, I would get y to the, well, 3 minus 3 is 0. But that seems a little strange, something to the 0 power. So what does that really mean? Well, I also know something divided by itself equals 1. So this brings up our 0 exponent rule. This says that anything to the 0 power equals 1. This means that if I did 5,491 to the 0 power, it equals 1. If the base was 5xy squared and I raised that to the 0 power, it would equal 1. If I said 4x to the 0 power, that would equal 1. Now, if I said 4 times x to the 0 power, that would actually equal 4. And that's because this 4 isn't part of the base. So x to the 0 power would be 1, and you would be doing 4 times 1 to get 4.